Good evening, everybody. Thank you all for braving the sudden cold snap to come and listen to me talk about large language models. I think we're good to start, right? I think we're on time. Got 150 slides, and I'm not afraid to use them. There's quite a lot to go through, so we'll see how far we can go through, how far we can get through before the evening is over. So, my name is Dominik Lukeš, and this is about how large language models understand text, or the questions of context and meaning in the age of AI. So this is me, originally from the Czech Republic. I was AI consultant at the Competency Centre. Before that, I was at the Center for Teaching and Learning. I ran a lab on reading technologies for reading and writing, and I wrote this report on AI, and I'm sort of keep track on AI for academic practice. And every second Monday of the month, if you would like to join the AI 6 special interest group on Teams, I do a roundup of AI news. So that's my job. But what nobody seems to want to, by and large, pay me for is to think about meaning and semantics and categories. And so this is kind of my lifelong obsession. So I translated this big book by George Lakoff, Women, Fire, and Dangerous Things, which is all about categories and particular way of thinking about language and meaning. I was also involved in critical discourse analysis and thinking about how people use discourse and language across big chunks of text. And so this is really, I want to come at the problem of how language models understand text by investigating how we understand text. So what this talk is about is kind of a little bit about what I did on my holiday. So during a holiday over the summer, I started this new blog on called Schemas and Propositions, where I tried to start outlining some of these questions around what I think the key issues around meanings are that are brought out to us about by the existence of large language models. So this session really is about being misled about meaning by our propositional attitudes. I'll explain what that means, but a warning, this is going to get abstract. So, propositional attitudes is an idea that I've came across from the philosopher Paul Churchland, where he said, our common sense conception of psychological phenomena constitutes a radically false theory, and it's so fundamentally defective that both the principles and the ontology will be eventually displayed. And what he thought in 1981 they would be displaced by is what he called the completed neuroscience. And large language models are sort of not 100% complete, but very close to completed neuroscience. But what Paul Churchland was really thinking about back then is this, that in other words, everything our brain, our normal introspection into our thinking tells us about meaning is wrong. For example, what's wrong with these two pictures? Yes? Yes, very good, yes. So basically, people don't run like this, like the foot that's forward, like that. It's the other way around, right? But it turns out when you ask people, show how you run in a static way, they do it the wrong way around. Including, and people, when you ask people to draw this, they also did it wrong. So including the official poster for the 1928 Olympics in Amsterdam had this, the artist drew this the wrong way around. And there's an academic paper that looked at this, and turns out people universally are really bad at recognizing the problem, and also they're really bad at demonstrating it the right way around. So it's just barely better than random, right? And so this is something we all run. This is something very natural, but nevertheless, just introspecting about how we do this is actually not a very easy way of doing it. And you can do the same thing for yourself if you ask yourself, explain an arbitrary rule of the grammar of your native language. Right? What is the difference between going to future and will future in English, right? You know, how could you explain that, the details of it? You probably couldn't. So introspection is really quite limited in what we can say about how we mean things. So that really kind of applies to our perception of how we mean things in general. But when people talk about large language models, there's a recurring theme that kind of goes like this. Large language models don't really understand. And so, for example, Emily Bender and Alex Hanna in their sort of book, The AI Con, they're calling the ChatGPT 6 the synthetic text extruding machines. Here's Hollis Robbins, somebody who says they're a scholar of language, saying large language models only operate in the realm of signifiers. There are no signifieds. So you see that picture of sort of the picture of a tree and the word tree. So she's assuming that we need to have some actual tree if you want to say tree and have some meaning. This is Bender again in that sort of famous paper that I think is mostly wrong about called On the Danger of Stochastic Parrots in 2021, saying basically a language model, back then it was just called a language model, is a system for just stitching together sentence sequences of linguistic form, but without any reference to meaning, or in other words, stochastic parrot. So that's kind of what most people assume. But I'd like to offer an opposing view. And that actually, this is something from a paper that I wrote many years ago, is that that was called, what does it mean when text really means something? So we say this thing, what does it really mean? And there's a whole disciplines based around sort of uncovering that question, but actually we don't have any good solid theory of what is the underlying meaning of text. So the textual evidence of conceptual structures is really multi-layered and quite difficult to capture. And I can sort of prove that to you if I show you, I remember this, reading this on a discourse, a textbook on discourse analysis for social psychology. So it's called Discourse and Social Psychologists. And so this is Potter and Weatherall, saying 10 stages of analyzing discourse. And so you kind of have all of these research collection, interviews, coding, validation, and in the middle analysis. So that whole thing that we think, what does it really mean that we're reading? They just say, well, just do analysis. And they say literally in that book, say, it's kind of like riding a bicycle. You just kind of use your language understanding and you understand language. And sort of you just try to make sense of it, right? So that's kind of the problem that we have, is that we're building on very simple, almost simplistic views of what language is like. And this was not obvious when computers first came. And the one thing that I'd like to sort of you start thinking about, when we think about AI, we think of this as kind of a separate thing that was happening alongside computers. But actually, the history of computing and history of AI are tightly interwoven. They're the same thing. And also, from the very beginning of people thinking about computers, they were thinking about the mind. And so here is the first thing that people heard about computers in 1946.
In 1946, moviegoers got their first glimpse of an astonishing new machine.
Are people becoming obsolete? A giant electronic brain has started cogitating at the University of Pennsylvania. It's made of vacuum tubes like your radio, and it can add up a column of figures a yard long in a second. It's the world's first electronic computer. Right now, it's solving mathematical problems for the U.S. Army, but who knows? Someday a machine like this may check up on your income tax.
Right? So this is basically, from the very beginning, people were suspicious about computers. They thought they're replacing people, and they kind of are using the idea of them thinking. Right? They started cogitating. So regardless of how good computers have been in the history of computing, people have been always using the same language. So you can hear the same language here that you're hearing now about AI. But some people are doing some deeper thinking. So this is Alan Turing in 1948 in a paper called Intelligence Machinery, which is a much better and more interesting paper than the one that he had the Turing test in, which came about 2 years later. And basically I was thinking, okay, so what would a thinking machine look like? Again, the term AI did not exist yet for another 7 years. And he said, well, actually, these are some of the places where the thinking machine might be helpful. So he had this list. Games like chess, bridge, poker, learning of languages, translation of languages, cryptography, mathematics. And he thought a thinking machine could do those things. And then a year later, Claude Shannon, another person sort of very closely associated with the developments of AI, made another list, and his list said he wrote a paper on how to program a chess machine in 1949. By the way, pretty much no computers. There's one computer you could do this on existed in the world. It was the Manchester Baby back then. So people were really thinking about computing and thinking long before anything like a computer would exist. And he was like designing filters, routing telephone calls, perform symbolic mathematical operations, and translate and make strategic decisions, and orchestrate a melody and perform logical deduction. So basically, all of these things in the minds of the early thinkers about computers and AI were the same thing. Now, a few years later, when there were about 500 computers in the world, Marvin Minsky wrote this thing about being puzzled about the discourse at the stage where pretty much no computers existed as we would recognize them today. He said, visitors to our planet might be puzzled about the role of computers around technology. On the one hand, you read about the wonderful mechanical brains that baffle their creators with prodigious intellectual performance. Or, on the other hand, the visitor would be warned that these machines must be restrained lest they overwhelm us by might, persuasion, or even revelation of truths too terrible to be borne. And on the other hand, our visitors would find the machines being denounced on all sides for their slavish obedience, unimaginative literal interpretations. So again, we're seeing pretty much the same people have been talking about computers the same way, regardless of what the computers could do. But people were very optimistic about having thinking machines, as you can see from Shannon and Turing, and Minsky shows a debate about thinking machines. But then we had that famous AI winter. And this was in the UK introduced by the Lighthill report in 1973. And the report basically says, we've had this sort of a pronounced feeling of disappointment. Workers that entered the field in the 50s or 60s with high hopes, in no part of the field have been discoveries that had any impact. Basically, none of the things that Shannon and Turing thought we could have machines do, they could do. Right? I mean, they could do some of them, but not very well. And this persisted for at least another 20 years. So this is Rodney Brooks, by the way, the roboticist and founder of Roomba. So if you have a Roomba or like that, he is the guy who did some of the foundational research and started the company. And he said, well, we're just going to having these so tiny little improvements. AI research is drowning in a sea of incrementalism. Right? So we've had this long journey of sort of thinking AI can do all of these things, but it not really being able to do them. And so enter the famous Moravec's paradox. So this was introduced by Hans Moravec, a researcher in AI. He wrote this in 1988. I think it was in an interview. It is comparatively easy to make computers exhibit adult-level performance on intelligence tests, playing checkers, but impossible to give them the skills of a 1-year-old, like recognizing faces or just kind of playing around, having a chat with each other. Right? So in other words, the Moravec's paradox is in AI, the hard things are easy and easy things are hard. Right? So that's kind of what we've had. And so if you look at the Turing lists, what are some of the hard things that are hard for humans but easy for computers? Well, games are hard for humans and they're easy for computers. Learning of languages, on the other hand, is hard for computers but easy for humans. And translation, which by the way, interestingly enough, Turing thought translation would be easier than learning a language. And that he was kind of wrong about that. Whereas cryptography, mathematics are easy for computers but hard for humans. And it kind of goes the same for Shannon. He had this sort of a weird list that just everything is all blended. He did not think at that time that these things would be different. And then there is sort of this really interesting premonition that Douglas Hofstadter had in Galois Shabak when he asked this question, will a thinking computer, he wasn't using the term artificial intelligence, but thinking computer, be able to add fast? And his answer, or sort of we call it speculation, says, well, maybe not. Because we ourselves are composed of hardware that does fancy calculations, but that does not mean that our symbol level, where we are, knows how to carry out the same fancy calculations, right? So in a way, you can think about our neurons are firing all the time. We're assuming that's what's happening. But we don't know that. We can say, oh, why don't you move over and fire with these other guys? We cannot do that, right? So we don't have access to that underlying level. Right? So this is what I think is a danger of thinking about AI as like it can do something or cannot do something because we're assuming we can do it. So in some ways, what we had in the history of AI, the next step is the propositional attitudes turn into a bitter lesson. And this is a famous essay by an AI researcher called Richard Sutton called The Bitter Lesson. Just a short blog post, but it has had such a big impact on the field in 2019. So that's before ChatGPT, before GPT-3 even. But he said we have to learn the bitter lesson that building in how we think does not work in the long run. So he was already seeing the early stages of the fact that when we try to encode our sort of propositional attitudes into models, it doesn't work. And he was saying researchers have tried to build in knowledge, and this always helps in the short term. It's personally satisfying, but in the long run, it just plateaus or even hinders further progress. And eventually, when the progress comes, it just comes through scaling, right? And then when we have that success, it's kind of tinged with bitterness because we're kind of assuming that the human-centered approach should be better, but it isn't, right? So we should stop, and he says, the actual contents of minds are tremendously redeemable complex, and we should stop trying to find simpler ways to think about the contents of mind, such as simpler ways to think about space, objects, multiple agents, or symmetry. Okay. So why are we having this disconnect between we think how we think and it doesn't work? Speaking of which, I don't have the quote in here, but there was an earlier quote from the 1980s where famous by the speech recognition researcher Fred Jelinek, who said, the more linguists I fire from my lab, the better my speech recognition gets. So that's kind of that idea of like, we're pretty bad at knowing actually what happens, right? And so this kind of brings us back to the question of, at Hollis and Bender and some of the others were saying, well, AIs don't really understand. Well, that's because I would sort of argue that basically they have a very simple meaning propositional attitude around semantics, which is that meaning equals representation. So basically, that if you see a picture of a tree and you say the word tree, those are kind of intrinsically linked, and you cannot have one without the other. But I'd like to offer sort of three types of semantics before we start thinking about language models. And the first one is logical propositional, and that's statements like what that's about meaning is what makes statements true. This is like a philosophical preoccupation, Russell and many others. True, false, and or, right? So those are the sort of like, is something true or false? What do we do if we combine these statements? And we can learn from rules. So we can learn that from rules that we just give somebody. So that's the sort of logical propositional things. And that's the representational semantics where we think, what do statements refer to? So when I say there's a tree outside, I'm talking about outside is over there, and there's a tree looks like that, so there's a tree, right? So we have things that like cat or run or red or government. You can learn that from a dictionary or a picture. But there's a second or third kind of semantics, which is relational, which is all about how do we learn things from context? How do things relate to each other? So that's words like get, the, how, or whom, or respect. And we can only learn them from context because, like, what is the meaning of the? What can you point at the? What's the representation of the? How do you learn it? Well, you can't do it, right? So basically, our propositional attitude, or the propositional attitude of statements like Hollis Bender is that if you say, certain number is true if and only if there is a picture of a tree. There's some sort of like a tree is like picture, right? So that's kind of what that is. So this is kind of that introspective or propositional attitude semantics. So we're assuming it's all founded in representation, relational is kind of irrelevant, and logical, and the representational semantics feeds into logic, right? So we're basically making true or false statements about things like this. It's here, it's not there, it's blue, right? So that's kind of what we think semantics is. It's all about truth, right? And basically, that assumption hides the relational semantics, right? And so we kind of have that preoccupation, philosophy is preoccupied with logical, science is occupied with the representational, and then linguistics or certain kinds of linguistics are occupied with the relational, with the famous words by John Firth about linguistic theory from the 50s that some people in AI says is the alignment of language models and linguistic theory, called "You shall know a word by the company it keeps." Right? And so this is the actual human semantics based on this sort of linguistic theory, is that actually it's all about, we have some representational experience of the world, that's fine, but it seeds the relational, which then shapes our experience again. And most of the sort of logical true or false stuff just runs on top of the representational or mostly relational stuff, right? And then most of the things we know about the world we've learned from context. If you think about all the things you know, most of them are of the nature you cannot actually learn them by pointing at them, right? And of course, there's the computing semantics, right? There's the computational semantics, which has been failing. That's why we had that bitter lesson. That's why we had the AI winters, because we thought we could just encode a bunch of, create a dictionary of representations, feed it into some sort of a logical engine, and all the relational stuff would just be in a dictionary. We're just going to put it all in a dictionary. And that just didn't work. And so what we discovered we can do, nobody really knew this would be possible. I didn't think this would be possible. I was very much wrong. Is that we could actually create large language model semantics where everything is based on the relational stuff. Just learning relationships between words gets us the level of semantics that's very much like human. So the seed, turns out, wasn't that necessary. And in a way, Rodney Brooks was presaging this again in 1980s, or this was 1980s something, right? Where he wrote this paper called Intelligence Without Representation, kind of thinking about, can we have intelligence without pictures linked to words, right? And the breakthrough of large language models is, yes, you can. We never thought you could, but yes, it turns out you can, right? It has limitations, but nevertheless, you can do a lot of stuff, right? So the question for us then, to think about ourselves and large language models, how do they understand text? What do relational meanings look like? And on a technical level, in the large language models, they look like this. They're vectors. So this is, again, the famous example that's overused and overinterpreted, basically saying, if you learn the relational stuff and encode it as these big vectors, you can do vector computations on meaning and have these relationships. So for example, if you take the meaning of king, and you add to it the vector of the meaning of king, the direction, and you subtract from man, you subtract from it the vector from man and add to it the vector for woman, using normal vector, just matrix sort of addition and subtraction, you get something very close to the vector for queen, right? And it's like, oh, that's very interesting. In fact, that makes it look like very sort of, makes it look very much sort of like how we think this might be, but actually this is what the vectors look like loads and loads of numbers, and we're talking thousands and thousands of dimensions, so that's why there's so many, right? But you can do normal, stupid, high school level vector math on these and get something like this. So for example, mother is to daughter like father is to son, right? And that you can go to the semantic calculator, all of that. So in some ways, people say that LLMs are statistics, large language model statistics, but actually they're more geometry than statistics. There are no frequencies inside a large language model. It's all these relationships, all these vectors. And funnily enough, one of the books that wrote about neural networks in the early, before they could do anything, which was for a long time, in 1969, by Minsky and Papert, was the subtitle, Introduction to Computational Geometry. So even back then, people thought about, this is actually a way of geometry, right? And so we've developed through the semantic stuff, through this relationship, we develop a semantic understanding. Now, what does it actually look like? And I want to contrast the thing to how people think this works and how it actually works. So let's try this. I'm going to give you some blanks to fill in. Let's see what they would like to just like be a normal prediction machine that isn't based on meaning. And just based on what you think is the most likely blank for that blank. So, walked in, what's the most likely word there in the blank? This one's easy, you have pretty much 50%. What? Walked in two, walked in, sorry? Walked in quickly, Another one, on, walked in. There's one that's the most likely, easy, walked in. No? Okay. Well, we'll see what it is, okay. Happy to help, okay. Clock showed 5, okay. At her, okay. Hello, right? So as you see, as we go down, you can basically not predict. Take your pick time, right? But basically, as you go down, you see just predicting the next thing becomes almost impossible because there's too many choices. Now let's try the same thing but semantically. So this is the text that these are from. So when all are walked in walked in the classroom, right? That's which was the most likely word. If you look at the frequency list, you would have known the is the most likely thing. Anyway, she was happy to see. The clock showed 10. Okay, somebody said 10 or quarter. It could be one of those. She looked at her teacher, right? Because you can have to read the whole thing going forward. Expectantly, hello. Right? So you went here from 0 chance of getting it right, or like sort of like tiny proportion, to 100% chance of getting it right. Right? The teacher said, nice to see you. You have started to take your work. Any others? What's that? Education, right? Seriously. Okay, so just think about what you were doing in your head. You were constructing a picture of meaning that made the fill in the blank much easier, right? So this is the actual truth. So Elara walked in the classroom. She was happy to see. Showed 10 to 8. So we couldn't have this 100%. She looked at her teacher again, 100%. Hello, Elara. And then nice to see you started to take your punctuality seriously, right? So that's an option, right? And so you have that. So if you think about what you were doing in your head when you were trying to fill in those blanks, that's what large language models can do now. Because if we ask, so large language model can have a similar semantic model of the world that you needed to fill in those blanks. And so, for example, if we try the n-gram, so these are called n-grams, by the way, just, so if you got this sort of bigram prediction on a large language model, it will do as well as you did, meaning quite randomly. It will not do very well. A much better tool, if you wanted to just know what's the most likely, it would be to use something like Sketch Engine, like a linguistic research program. But if I ask a large language model, in this case, Gemini 2.5 Pro, to do this, it gets it exactly right, exactly the same as you. It can do exactly the same semantic things you can do. And then in fact, if I ask it, can you give me some alternatives, it even can it thought of something that none of you thought of, punctuality. It thought, hey, punctuality could be in there, right? So it's actually quite a good sort of a tool for this sort of thing. Sorry, I'm just trying to get the right. And so the question to us is, where has the semantics come from? Right? Where is all of this coming from? Where does the meaning come from? And we often say it was just trained on all of the internet. And I don't have time to talk about this, but basically there are 2 stages, and one of them is pre-training, where it learns the relationships, the relational data, and then the other one is post-training, which is on a much smaller task where it kind of learns how to follow instructions and how to exhibit personality and so on. So we don't have to talk about that. But basically, what are the mental structures you need to have in your head to be able to make those, fill in the gaps? And by extension, what is the kind of thing that the large language model has to have in its quote-unquote head? And the best way to think about this semantic prediction is the word schema. And schema is the one big sort of breakthrough that again came out of the idea of AI, came out of the research in AI, but also those of you who are psychologists, you may have heard about Gestalt theory, so it's kind of inspired by some of those same ideas. And this comes from a collaborator from the 80s of David Rumelhart of Jeff Hinton. So everybody's heard about Jeff Hinton by now. but actually, Ronald Hardy was doing the much more interesting work back then because he was a psychologist and neuroscientist as well as a computer scientist. But he was basically saying schemas are the fundamental elements upon which information processing depends. Right? And they were rediscovered over and over again in different aspects. So there's people talk about scripts, plans, and goals and understanding as frames. Marvin Minsky wrote about frames, but also people in psychology were talking about framing and mental models and so on. So all of a sudden in the 70s, we realized that, look, this computational stuff, this basic understanding of meaning as a computation of sort of reference, of basic reference doesn't work. And so this came back into AI as something called the Vinograd Schema Challenge. Terry Vinograd was one of the early thinkers in this area. And basically he said we need world knowledge and reasoning for the resolution of the problem. So here is the famous example in the Vinograd schema. The trophy did not fit in the suitcase because it was too big or too small. So when I say it was too big, what does the word it refer to? Trophy. And when I say it was too small, the word it refers to suitcase. And you know that immediately. You don't have to think about it. You don't have to write some sort of a program of inference. And in fact, it's impossible to do it almost by programming. You need to know things like what's the typical size of a trophy, suitcase size, relative size of a trophy, and suitcase, but also the principle of containment. Bigger things cannot fit into smaller things, right? And so you can have this sort of a basic type of reasoning. You can think about it as a logical reasoning, but you kind of have to have quite a lot of world knowledge because this seems simple, but people who were working in the frame semantics area in the 1990s developed this idea called FrameNet to make this easier for computers, and they thought, let's encode all the schematic knowledge you need to have about the world to be able to reason about things like suitcases and trophies. Anybody? Well, you cannot see the problem, but I'll tell you what the problem with this is. Nobody said in their definition of the frame of containment, they didn't say containers are bigger than the things they contain. It's nowhere there. It's just so obvious. Nobody thought that would be a thing to worth encoding. But that's the thing that's there, right? So when we think about the sort of the signified, we actually think about, we should need to start thinking about it schematically instead of just like a picture of a tree. So when you have, when you use that same word, a tree fell next to our house, it has a very, very different meaning from a leaf fell next to our house in pretty much everything that matters, right? For you as a meaning, because what would be the next sentence? A leaf fell next to our house. Well, and what? So what? Whereas a tree fell next to our house. What happened? Right? Did the house get damaged? Did somebody get hurt? Right? Right? So basically, we're learning that these meanings are all, the LLMs can all do this. Large language can all do this. But also we can start thinking not just about the signifier, but also the signify, not just the signified as a schema, like the meaning, but also the form as sort of a schema. And this is kind of this is the first time that the word hallucination was used in, I think at least, 2015 by Andrea Karpathy. And he said, and it was used in a positive way, he said, in case you were wondering, the Yahoo URL doesn't actually exist, the model just hallucinated it. But his model was really dumb. It could do almost nothing. It didn't have any reasoning. But he was so amazed that it actually could produce a valid link, even though it wasn't real. That was a major breakthrough that models can do this. They kind of can think of the form. They've realized, okay, there's a schema for this form. I can learn what that schema looks like and follow it. And you can play around this when you play with really, really small large language models. Like, for example, this is Qwen 2.5. And if those of you, I'm assuming nobody here speaks Czech, but basically this is asking it to write the Czech parts of speech. And it's hilarious because this is what Czech parts of speech could look like, but they don't. It has like a vague shape of it. And so I always play around with this because I find it very, so just kind of like sort of verby things or or moving things. So it has all of these things. So basically the model hasn't learned the actual words, but it has, because it's very small, but it's learned the shape of them. What does that sort of thing look like? And as it gets bigger and bigger and bigger, it actually can do this. So the large language models that you have in ChatGPT can do all of that, right? So I think that's our problem, is that when we thought, can we take all the knowledge required for things like that and listed in a set of logical propositions, when people have tried, like the famous psych project, CYC, and it fails. It just, they thought, oh, we just need a few million of these. And it turns out they were on, and one day, after a few years, they had 10 million, and they were still not anywhere near, and they had to scale down what they thought they could do. But things are even more complicated because there's more, so we could think, with these schemas so far, we could actually probably write enough statements about them down. But what about a statement like this? That's another Vinograd schema challenge. It's a very different kind. The town councils refused to give demonstrators a permit because they feared/advocated violence. So if the word is feared, who does they refer to? Councillors. And if it's advocated, who it referred to? Demonstrators. How do you know? How do you know it so quickly and effortlessly? And it's because the world knowledge is not in the words, but it's in the whole picture, right? You understand the whole picture. So you understand the roles of people involved, the motivations, the sequence, the scripts of the events, the social conventions, organization, legal facts and understanding, right? So all of those things you have to know, and it just kind of happens like that, right? So it's impossible to make a list of logical propositions about a statement like that you could encode into a computer. And it turns out when people tried, they failed. You could never, the early Vinograd schema challenge, all the language models of the early days when this was developed, they basically were failing until we had large language models who all of a sudden can do this. They somehow can marshal all of this knowledge and understanding to do with this. And this comes up in many more contexts. So for example, I just watched Rodney Gentry on YouTube and I thought, I drink too much. The last time I gave a urine sample, it had an olive in it, right? So what does it take to understand that joke, right? What do you have to know about the world, where so drinks have olives in them, and that, where does that sort of, but obviously also know that that's, you cannot, the olives don't come into the drinks through urine, right? So we need these schemas basically all over the place. That's kind of how we understand text. And it turns out if you ask a large language model, does it understand that joke? The answer is yes. It can explain everything behind it. So that in a way is, we're kind of using this to understand text. Okay. But it gets more complicated. So far I've just going to try to show you that meaning is more complicated, and large language models can actually have very similar kind of meaning like we do. And so I now want to talk about tools. So how do the schemas show up when we do tasks with text, such as how do we do things with reading? So I'm going to ask you a question in 2 seconds, and I'm about this text. And the question will be, how many women are mentioned in this story? And I helpfully highlighted all the people in that story in bold. So I'm going to give you 2 seconds to answer that question. What's the answer? 2, yeah, right? Okay, how about the next story? How many women are mentioned in this story? I'm going to give you 5 seconds. What's the correct answer? 5, right? Did everybody get 5? Okay, again, right? How about this one? How many women are mentioned in Pride and Prejudice? What's the correct answer? You don't know, right? What would it take to give you, for you to get the correct answer, right? And so what we see here, we have sort of 3 levels of tools that our mind needs to answer those simple questions. So on the first level, attention, you just look and you knew, right? So 2 was you just needed a second. The second one, you actually needed to kind of look and with your mind kind of like make a little checklist in your mind. Whereas with the second one, you need a tool. You need to sit down and say, okay, read the first line, is there one mention, make a note, and just kind of take go through that. It would take you forever, right? So that's what's called the cognitive load. So you start with attention, you're just going to look at and do something. You have working memory as kind of a mental checklist, and then finally you have an external tool like a paper checklist or some sort of a computer, right? And so basically you can think of it when you're in a supermarket and your partner calls you and says, buy milk, and you just reach for the, walk over where the milk is, pick it up. That's just attention. You don't need to think about it, you just do it. But maybe they say, buy milk, cheese, and eggs. They say, oh, okay, milk, cheese, and eggs. And you can walk around and say milk, cheese, and eggs, milk, cheese, and eggs in your head. You can do it in your head. And then they say, soy milk, hard cheese, 12 eggs, brown toilet roll, 2 lemons, beers for all guests, and all that. All of a sudden, okay, hold on, I need to get a piece of paper, right? So that's kind of how that works. And so how does a large language model do all of this? Well, it only has attention. Famously, the paper that introduced large language models was called Attention is All You Need, even though it's a different kind of attention. And basically, it doesn't have mental checklist. The large language model doesn't have a mental checklist or a paper checklist. It has to do everything with attention, which means it often struggles with, right? So the way the models work, when they look at text, they don't have a mental checklist to go through. So for example, often people say, give me, proofread this whole text. And we know when we proofread something, we're just going to have either a mental checklist or a real checklist. I've done this sentence, I've done this sentence, blah, blah. The model cannot do it, doesn't have a mental checklist. It can do a pretty good job, but you cannot trust that it looked at everything, right? So for example, when I gave that same, like a very small language model, when I said the same task to how many women, so it was able to count 2 women and 5 women. So when the text is short, the attention, the model can do with attention even the things you need working memory for. And actually, it turns out when I paste in Pride and Prejudice into Gemini, which is a long context window, it can tell me about women, all the women in there as well. But all of a sudden, because it doesn't have a mental checklist or any tool, I cannot trust it. I can trust it about as much as I would trust a human just kind of reads it and makes a few notes, right? So it's quite hard. But sometimes the models are pretty good at this, even if they're better than humans, even if they actually are bad, right? So for example, they famously cannot count words in text. So if I show you this, how many words are in this text? Yeah? Any guesses? You have to guess. It's like 200, 300, something like that, right? Well, if I ask a large language model, it's about as good at it as people. It says 224 or 300, and different models can give different answers. The actual number, if I tried it in Google Word Count, is 242 words. But actually, if I use ChatGPT and I allow the use of tools, something called code execution, where it loads the actual text into a piece of software, it can give me the correct answer. So in here, what ChatGPT did, instead of use a tool like humans do. So instead of like you would use Microsoft Word perhaps for counting words or something like that, a large language will say, I'm going to write myself a bit of computer code, load the text in, give the correct answer, and it gave me the correct answer. Right? So again, it's the questions with sort of tools that we have available versus the model. So we're kind of, when the model looks at a bit of text, it can kind of do about as well as us at giving us answer. It can even answer questions about like how are the different women mentioned, how are the different, what is interesting about the different women. But again, the model doesn't, when it does do that about like Mr. Darcy and so on, when the model does do that, it again doesn't have the mental checklist. So it's going to have to be a bit cautious about how much we can trust it, but nevertheless, it can do the sort of semantic things that people can do. And we often say, well, actually humans are really much better at this and we can trust humans and we cannot trust large language models, but actually, even when we do use tools such as other people like proofreaders or sort of our attention and everything, we get things wrong. So here's a sentence from the AI Con, where it says the Time magazine reported that OpenAI had subcontracted Kenyan workers making less than $2 a day. Anything seems off with this? Anything's wrong? Any sort of intuitions why that? What could be wrong with there? This. The headline of that paper says $2 an hour, right? And that's a big difference. It's an order of magnitude difference. And this is in a book that was published, and it says that AI is really bad at this. And also this had proofreaders and people fact checkers. Many people looked at this and nobody noticed this error, even though this was right there. This wasn't a hidden thing. This was like the title of this $2 an hour. And if you ask a large language model, does it have enough knowledge to recognize that this could be a problem? Then actually it turns out, yes, it can look at the text and give us the correct answer about that text. But even if you ask a very dumb, tiny language model to say autocomplete a sentence, workers reviewing AI models in Kenya, it will say $200 a month on average, which is about $200 an hour, $2 an hour equivalent. So that's an important thing, right? And so Bender and Hannah in their sort of paper, why did they make this error? Well, they made the error because the schemas in their head were overriding the context and sort of leading to what's called, the attentional blindness. And where do the schemas come from? Well, they come from, if you look at the corpus and say live on blank dollars a day, you'll see that by far the most common usage there is live on $2 a day, right? So that's kind of that. That's where those schemas come from, right? So in some ways you could say that they basically, there's a little bit of a hallucination happening with humans. So we're having that sort of very similarities and differences. So in some ways, the language models, when they read text, they kind of do very similar things to us. They look at meaning. They're primarily semantic processors. And so we're looking at the similarities, and let's now look at some differences. So what is the fundamental difference between humans and large language models? And the answer lies in the 51st Dates film, but also in the P in ChatGPT. So what does ChatGPT stands for? So chat, the G stands for generative, as in like generates text. P, pre-trained, is just trained once, and then T, transformer, which is the attention bit. But basically, the key thing is it's only trained once. In other words, it does not learn continuously, which is the big difference between humans and large language models. And the reason I had that picture on there is because it's famous again. It's a romantic comedy, 10, 15 years ago, of Adam Sandler and Drew Barrymore, where Drew Barrymore, every time she falls asleep, she forgets everything that happened until she had her brain injury, because she had like an accident, and so she cannot retain long-term memories, and every time she falls asleep, it erases her memory. That's a made-up condition, but there's a similar kind of, there are conditions like that, right? And so basically, you can think of it, she was just trained once up until the moment of her accident, whereas he hasn't. And the whole plot of the movie is, it says, well, they have a really nice first date. So how do they actually progress to marriage and eventually having a child? And the final scene of the film, or her name is Lucy in the film, is that where she wakes up and then there's a video and says like, watch this first. And presumably that video tells her the whole story of their relationship, up to including them having a child, which kind of shows up in the, right? And then she walks up on deck and says, oh, she's very happy. Right? So just imagine, what would the video have to look like to contain all the sentences you need to know about your life that leads to falling in love, having a child, and just getting a husband, right? So what would that look like? But actually, that's what every time you interact with a large language model, that's what the large language model is. It doesn't have any memory of any past interactions. I wrote about this on the blog if you want to follow up, right? And this whole thing, so the whole thing is, basically the whole problem with this is that if we want the large language models to behave like we do over the long term, we have to deal with the problem of tacit knowing, as Michael Polanyi, formerly of Oxford as well, wrote, as there are things that we know but we cannot tell, right? So that's kind of the Drew Barrymore problem, Adam Sandler. How do you express all the things you gather from an experience, a lifetime interaction, in a few sentences, right? And the large language models at the moment only have the knowledge up to the moment they were trained, and there's nothing new, right? And so this has a practical problem, is that, for example, in a recent study, it turned out they were really bad at helping developers with existing code bases that have long history, because developers often rely on undocumented knowledge, and AI lacks this tacit code-based knowledge and has no way of developing it, because it can only look at things it's seeing in front of it, right? So this is actually how the large language works. So so every time it generates an answer, it actually uses all of this context to do it. It doesn't remember the beginning of the conversation. And it's always some sort of a list of propositions. So for example, when I ask it this question, I have this long conversation. When you have a conversation with a person, your mind is forming this sort of a picture of that conversation, whereas a large language model needs the whole thing sent to it again and again. So every time a ChatGPT answers a question to you, you actually, inside of a chat, it doesn't have any memory of it. It doesn't sort of retain anything. Between chats, between the sort of turns in the chat, it needs to have that whole history of your conversation sent back to it, which is why, as the conversation gets very long, they get more erratic, because they don't really that much. They're pretty good these days. But nevertheless, there's more of a chance that some of the stuff goes away. So the problem we have is the problem is really about context. And we process context differently from large language models. So large language models, Humans, when we have a long context, in the sort of the recent, like a conversation or a text we read, or when we develop schemas of the conversation. We don't actually remember everything that happened. We're just going to have this picture of what happened. Whereas and then we also remember some of the things we said, but the models don't have any new schemas. They just have the things they were pre-trained plus these new, a list of propositions, list of sentences. This is exactly the conversation we've had up to now. Right? So the fundamental problem that we have in the future of large language models, because they have a limited context, I mean, they're pretty long. The context window is about 1 million tokens up to thereabouts. But it's how do we choose the right context for the language model at the right time? So I know when you're having a problem with ChatGPT, often you have to think about what is in its context right now. What is it seeing in its context? It's because it doesn't have any other memories, right? So how do we compress the things we know but cannot tell into sentences? And this has now become known as context engineering. Right? So in conclusion, the answer to how do humans and large language models understand text, how they read text, is that we process meaning in schemas, and we've seen that, but we communicate in propositions, and the fundamental difference between the two is online learning. Right? It's the fact that we learn all the time. We're developing new schemas all the time. Your brains right now are different than the brains you had when you walked in. Mine is as well, right? Everybody's brains are constantly changing. When you have a conversation, when you're eating an ice cream, your brain is constantly changing. The connections, the synapses in your brain are changing all the time. The large language models, no matter how much you interact with it, is always the same. And that's a big difference. But nevertheless, when you think about large language models, the last word is beware of your propositional attitudes, because they can also lead you to wrong assumptions about how you and large language models work. But nevertheless, I think we have some time for questions, so thank you. Yes, there's a microphone coming your way.
Thank you. That's a fascinating talk. Thank you. Is one strategy to try and get over the lack of context to create a custom GPT and front load it with loads of files and specific context you want it to remember every time?
Well, yes. Well, no, yes and no, right? So in some ways the context, because you're just giving it facts. So imagine you have a new employee coming to your organization or your department, and the previous employee who they're replacing wrote down everything they know about their job. And you give that piece of paper or sort of like that booklet or whatever it is to the new employee. Can they do their job based on that? And the answer is, of course not, right? It's impossible to write down everything you need to know. You at least have to spend a bit of time, like go meeting people, talk, learn what those things mean. So in a way, the GPT has the same problem. What you can put in a GPT, you can put that booklet of the previous employee, this is what there is to be known, but it only works if it has all the information you need. Now the GPTs are even sort of more deceptive, because if there are too many documents in the GPT, in a custom GPT or in a custom bot, then all of a sudden they don't all fit. So the large language model cannot see them all when it's generating an answer. So there's another process called RAG, Retrieval Augmented Generation, that tries to match your question to snippets of those documents and bring those snippets together, send them to the large language model's context, and say, based on these snippets, answer this question, which is often very, very useful, but also dangerous because it doesn't see the whole context. So you cannot ask a GPT compare these two documents out of in a library of 2000, for example. So that's the limitation. So yes. That's the problem. You have to decide, okay, what goes in the context at what time so that I get the right answer at the right time. And at the moment, it's if you use AI-assisted coding and create sort of applications with AI, that's where it's most keenly felt, because often you run out of context and then the AI starts writing another application inside another application by mistake. So those things can happen as well. Sorry, there was another. There's.
Thank you for your fascinating speech. I'm a DPhil student in Big Data Institute. I'm really curious about, because the fundamental function of the LLM is to predict next token through the simulation of distributions. But it has been claimed by some company that it has been used to facilitate researches like finding the drug targets or discovering new mathematics theories, but it can only use to predict the next token. So how can it be so innovative in such difficult tasks? Or do you think it's the ultimate architecture of the LLM, or maybe it can pick up some logic or representations which we humans normally do?
Yeah. So I think the word is wrong. I think it's wrong to say that LLMs just predict the next token, right? Because what does the word predict mean, actually? So most people think about it, again, there's some sort of like a statistical distribution that you're predicting over, but the models, in a way, they had to learn something that isn't frequency-based, right? There are no frequencies inside a large language model. And actually, it's almost as accurate as saying, you know, when you're reading a menu in a restaurant, you're predicting which meal you like the most, right? You're choosing the next token based on those relationships. Now, and the prediction actually comes in the training process where you use a reward function that's used to train the LLM based on basically, did you pay the right token next? But when the LLM is when the neural network is being, so the backpropagation algorithm isn't adjusting frequency, it's adjusting weights in a way, kind of like a geometric way, right? So basically, I think it's wrong to say it predicts the next token. But also, even if it did, there's a bit of randomness, and you can just say very easily, how do you generate novel ideas? Well, just roll a dice, and that gives you a bunch of random numbers. You can generate lots of novel ideas that were never used before. But because the large language model actually isn't doing it in that way, it's sort of semantic, you can generate things that are new. So don't get tied. So we often say, oh, it just kind of predicts the next thing based on the training data. But I don't think that's a useful way of thinking about it. Think of them as basically semantic machines, and therefore they can sort of create new ideas just like you can. The problem is we often have the wrong propositional attitude around how we generate new ideas. And that's where the schema thing comes in, right? So how do you, as a researcher who's going to spend years of studying a problem, how do you generate a novel idea? Well, you do it once out of hundreds of times, right? So in a way, it's like not everything you generate is new or is novel or innovative, because you couldn't. I'm just like, you'd go crazy, right? So often we think, oh, we humans are so good at being creative, but actually we're not very good at being creative. We're good at being creative like one out of so many times. And because we have that continuity, it feels like that's all happening in our mind, but the large language model doesn't have the continuity. So all we can do is just kind of ask for many times, and in one of them, select the one that's most appropriate. So I don't think there's any sort of discrepancy. It's easy to generate novel things. The trick is selecting the ones that matter, right? And I think the models are not as good at that because they don't keep the schema. They don't have that sort of the continual learning, but they're pretty good at it now because they're pretty well pre-trained. So I think that is where the schemas versus propositions idea come from, is that sort of continual learning versus sort of like learning once and then like starting every new interaction with the idea, with the subject anew. Sorry, there's a microphone coming your way. I think you do, because for the recording they need it.
So you said in the early days translation was a big issue. Tell us about where do we stand with that now? Because in business we use LLM translation tools, and they only ever reach 75%, and our constant problem is, yeah, but a native would never say it like that.
Well, it really depends on the language and the context and what they're translating. So one of the issues with large language models is that they can only output so much text, right? And so you cannot like put in a whole book and ask for that to be translated. You can sort of put in, I would say, sort of a page level text, or maybe like a few pages. I mean, as a translator, I don't think that's true at all. That the 70% is true. I think it's much better than that. But also, I've sat in so many linguistic seminars where people were just sitting around and says, oh, I would never say that. And so no, I would say that. So basically, never trust people when they say, particularly when they're not, like they haven't done proper research, when they say, oh, I would never say that like that. Yeah, you probably would. And often people would, in the next sentence, they turn around and say it. So basically, I don't particularly trust those statements like off the cuff. I think it's much better off than 75%. It really depends, again, on the purpose, but also humans are really bad at translation. So much of unless you're really trained to pay attention to those correspondences. So I like a good, in the 90s, like a good sort of a preoccupation of mine was to watch Czech movie, English movies or American movies dubbed into Czech, and just see egregious errors that people made in there just because of misunderstanding idioms and misunderstanding context and so on. So we're kind of have this myth of like human being very good at this, and they're pretty bad, and even professional translators make mistakes. They make slightly different ones, but I would say we're now at a stage where the LLM powered translation is pretty good, depending on the language, depending on the context. So you still have to be a bit careful. But I would say they're closely on par with, definitely on par with just somebody who speaks both languages. And the very, really good professional translators will still be better. But nevertheless, I think that's, again, it's the semantic part of it has been solved. There's still issues, but yes. Yes. Sorry.
Thank you for your presentation. You were talking about cognitive offloading, and that this is probably one of the biggest threats to human learning with this type of technology. In the past, you would have computers, calculators, but now humans are delegating so many tasks beyond the ones from the past. So what's your opinion on that, and how to make that process less harmful?
So I don't think I said that, and I don't think I talk about cognitive load, but I don't think that's, again, I don't agree with that almost at all, because think about when you were in the old days, and you were really, really successful in business, and you had an assistant, a personal assistant. What do you do with a personal assistant? You offload as much as you possibly can onto them so you can focus on the important things. Are you becoming stupider as a sort of a captain of industry, right? So you dictate to that person, you ask them to keep meetings, to keep notes, right? People make minutes, right? So people have always been doing that. And so I don't think that's necessarily, I don't necessarily see the big danger in here, because we've always had something that used to be important that now isn't. Many people forget, I don't know, probably not in this room, that the word computer used to be a job. Right? My grandmother was a computer is an actual sentence you can say, and it can be true, right? And there were like loads of rooms full of like kind of like this. During the war was women, but before that it was like men adding and multiplying numbers, right? Just like doing one after the other, right? And because what was happening is that the army, the people who wanted like ballistic missiles and other things, well, they needed to cognitive offload to that room of people, and eventually that room of people was replaced by one big machine. And then before that we had sort of log tables, and we've always tried to offload the cognitive load as much as possible. And people have always said this is going to be the end of civilization, because people will forget how to do the things like reading, right? So that's why people famously, it's kind of slightly overblown. Plato was saying, Socrates saying, I don't like this book thing because people will stop remembering. So I would say, and yes, people actually stop remembering things in certain ways, but by and large, smartphones have, there used to be a time where I remembered phone numbers, right? I mean, many of you are too young to remember that, but I remember when I had to I don't anymore. It's all uploaded onto my phone, and it's fine, right? I mean, I haven't gotten noticeably dumber, at least not because of that. So I don't think that's a problem, because people's cognitive sort of scope is so great that we can always find something to focus our cognition on when we offload things. That's not to say that we won't lose some of those things that we thought were important, but because we have the tools, we won't necessarily find them as important as all that. So that's kind of I would not worry about it as much.
Yeah, I was just wondering why LLMs are so good at coding, and was that deliberate or a kind of accidental thing?
Well, the whole thing was accident, right? So attention is all you need was actually a way to improve machine translation. And all of a sudden it's like, it can answer questions, it can do styles, it can do all of these things, right? And so all of a sudden you have these sort of general weird semantic engines. And it turns out one of the languages, it can speak as code. And it just, the large language models basically have a semantic, that's sort of the weird sort of semantic, the sort of signifier is just kind of blurred. And they can do it. It's just one of the languages it can speak. Now, why they're so good at coding now is deliberate. So the initial sort of thing it can do this is like, oh crap, who knew this could be done, right? And so you could see it in a carpathy. It can do a URL, but maybe it can do more, right? So I think the initial was kind of like an accident. You can just like it can do everything. It can do coding, but all the progress in the recent like companies are focusing on it. So what they do in the post-training phase I alluded to, they have loads and loads of examples of good code and coding processes, and they also give feedback from what's called verifiable rewards, because code, unlike like philosophy, you can actually say this was good code because it ran and compiled or whatever. And so that's, yeah, so all of the recent progress in coding tools has been deliberate because it's a major driver of progress and sort of revenues. And I've been making so many applications using large language models recently. I love it. So it's really progressing fast. If you go to my website, that one was entirely made using a tool called Lovable, and I did not write I used to write code for websites, didn't write a single line of code, just like, this is what I want my website to look like, make it. And there's like, and here's the content, and put it where I want to tell you to put it. There's no CMS behind this website. It's just entirely me telling a large language models, make it pretty, make it look like this. Here's the content I want in there, do it. So that's where you can kind of get all of those things, yes.
Hello, thank you. My question is in the general sense of interacting with large language models, because you alluded to the fact that they could come up with new ideas in some way. So since they have access to all of this information and they can draw parallels, is there a reason why we have to prompt them to think about drawing these parallels? For example, if I say my cup is either in the room or in the kitchen, and then you check the kitchen and it's not there, you would assume that it's in the room. So in the case of LLMs, if they've seen all the data that we have available about biology, for example, why can't, not why can't, but like the current user experience of interacting with an LLM is thinking of a question and then you ask it and it looks for an answer. Is there something inhibiting in their architecture, in their implementation, that stops them from just suggesting that, based on all of this information that you've given me, have you considered this as a cure for cancer?
Well, so what is a large language model? Large language model is just a bunch of numbers. And it's a file that sits on your computer. I have about 10 of them on this machine. It's really easy. If you have like an entry-level Mac, you can have loads of them, play around with them. And it just sits there. It's just like, it's not thinking, it's not waiting for you to ask a question. It has no sort of agency. And so again, what we forget, let's get back to propositional attitudes, you forget that when you are sort of solving a problem, you constantly have this feedback loop, and your chat never ends, right? You have this internal chat, but again, even when you sort of go get ice cream and talk with your friends about whatever something else, your brain's still there, right? It's still processing. Your brain never stops, right? You go to sleep and things happen. You wake up, oh, now I know it, right? So the large language model, no, it's just like a bunch of numbers, and it's only doing any quote unquote cognition while it's generating tokens and it's looking at the context. And so when that goes away, it just stops. There's nothing is happening. So all the things that we often attribute to our kind of like these insights of brilliance are actually a result of a continual engagement that's happening with our brain all the time, developing new schemas and having also bodies that kind of move us to, oh, let me go look at over this and look at this. We have agency. We have sort of like long range tasks where the models don't. So that's why you need a prompt. You need to say, look, here's the context, and just keep generating stuff, right? And that's we experience it as the model kind of thinking or speaking to us, but it's not really. It's just generating tokens it uses the semantic understanding to be able to do it. So you think of it as a semantic engine, but it's just an engine. It's not a being, right? So it doesn't have any continual existence, and that's the biggest problem that we have. So that's the reason. So can we have one more? I see, but there's the last one. So I'm seeing sort of already. But I'm happy to stick around and talk afterwards. It's hard to stop me.
Thank you. I guess so. Following on from what you were saying just now about we have agency in a body and we move around and we learn things, and I guess at the moment the ability of an LLM to process meaning, represent it, is dependent on being trained on text written by humans, which is informed by that physical experience. So I wonder if in future increasingly AI is trained on text generated by other AI.
Oh, this is on the future. That's now. That's happening. Yeah. No, it's still the same. Basically, we got to a stage where the language models can generate good enough text people have probably heard about the model collapse when you sort of train the model repeatedly. That works on small models and when you just pretty much just do model-generated text. But when you insert synthetic data, all the progress in small large language models is done with synthetic data generation. That's already happening. It doesn't make that much of a difference because it's just more of the text, right? So it doesn't particularly seem to make much of a difference. Yeah, and so. And again, it doesn't particularly matter it was trained on the human text. I mean, so the last kind of warning is that never make assumptions about why a large language model did something or didn't do something based on what you think the training data might look like. Sometimes you can make sort of general things like, oh, it wasn't trained on like who's the prime minister now, so it won't know who the prime minister is now because after an election, that's fine. But you cannot basically look at say, oh, this is because the data is like on this internet, like this on the internet, that's why the models are like that. Because there's so much garbage in the training data and the models can just kind of figure out the right things through it. So I would say don't think too much about it because the training data, the current state of the art is not just dump a lot of data in. It's what's called curriculum learning. So you choose the order of which, how often do you show certain things versus other things. And so that's kind of, you can, again, if you go to the Google, if you come to one of my updates, I often talk about like there's a new model came out and people describe how they do this, so you can go, or the generative AI SIG, I often post about that. So basically the bottom line is the training data is much more complicated than just dumping all of the internet in the model. It's kind of one of the big things that's happening right now. So it's hard to make any conclusions based on that. Oh God, we ran so horrendously over. I apologize from the bottom of my heart, but thank you so much.